Sorry, I forgot. I got so excited to do the math, I forgot to start recording. Okay, so we're looking at finite differences, just a little recap. Depending on the highest exponent of x, the degree of the power equation, the power function, will tell us what finite difference we should have and what that finite difference represents in terms of a. Now, there is a trick to figuring out what that nth finite difference is, and it is using the factorial symbol. So let's talk about that. And again, most people don't really talk about this, but it's a nice symbol to know because you never know on a standardized test if they're going to give it. So we said when n equals 1, it was linear. And the first finite difference was a. N equal 2 was quadratic, and the second finite difference was 2a. N equals 3, it was cubic. The third finite difference was 6a. N equal 4, let's say, was quartic. So the fourth finite difference was 24a. So where are we getting these coefficients? So this is 1, the coefficient is 1, the coefficient is 2 of a, the coefficient of a is 6, etc. So how am I using these numbers to get these numbers? I'm using the factorial symbol. So let's go ahead and take a look at that. If n equals 1, I'm going to calculate 1 factorial. If n equals 2, 2 factorial, 3 factorial. So depending on what your degree, your highest exponent of x is, that's the factorial that you're going to take, so we know what that nth finite difference is. So what is this mysterious factorial? It's telling you start at that number and count down to 1 and multiply those values. So 1 factorial is just 1. 2 factorial is 2 times 1. 3 factorial is 6. 4 factorial, do you see how I'm just counting down to 1 and then multiplying? So 4 times 3 is 12, 12 times 2, 24. So what if I had a quintic, meaning 5th degree, n equals 5? What would that 5th finite difference be? You tell me.
Would it be 120?
Yes, it would. Does everybody see that? So that would allow us to get the leading coefficient. Nathan, does that make sense?
Yes, ma'am.
Yeah, isn't that cool? That's cool. I mean, that's super cool. That little factorial symbol. Now, if you've taken statistics, or if you're going to take statistics, probabilities, you'll see this little factorial. You'll see this. This will come up. So, I mean, this is a nice little, I mean, this is super cool. This little factorial thing, that's super cool. Okay, so I just had to share that with you. Was that neat? Okay, all right. So we've talked about that. We've talked about factorial. What I would like to do, because some people have expressed their discomfort, let's say, with graphing. So what I would like to do is I would like to go back and maybe we graph some linear functions. I'd like to go back and graph some of the quadratic functions, shall we? Let's graph some of the quadratic ones. So let's go back and let's find one. Well, let's do the first quadratic one that we found. So number 9. So if I look at number 9, the equation was y equals x squared plus 2x. Now, if you want to get, I know you have graph paper in your packet that you got. So if you want to get graph paper, you can get graph paper. You can do it on a blank sheet of paper, but if you want to be super accurate, graph paper would be bad. I'm just going to do it by hand on a blank sheet of paper because I don't think I have graph paper on here. Boy, that would be cool though. Okay, so number 9, the equation we had, can somebody tell me what that equation was again? Number 9?
X squared plus 2x.
Okay, so state the entire equation. You are correct, but y equals x squared plus 2x, because for it to be a function, you have to have the input and the output, the domain and the range, so x and y. So let's investigate this. Let's investigate this function. I know the graph of this quadratic function is going to be what? Do we know? What do we know the graph to a quadratic function to look like? What is the shape?
Parabola.
It is a parabola. Now, my question to you then is, you say it's a parabola, that little U shape. By looking at this equation, do I know if that U opens up or opens down? By looking at this equation, does it open up? Does the parabola open up or down?
Up.
And how do you know that it opens up?
The positive 2.
Close. The fact that the term that you are looking at is positive tells you that it opens up. But we are looking at A. A. What is A? Remember, A is the leading coefficient, right? So it depends on A, Nathan. So you had the right idea. But if A is greater than 0, the parabola is opening up. If A is less than 0, the parabola opens down. Do y'all remember that? So it's all a matter of the sign. Let me do that in yellow. Of your leading term. So you were close, Nathan, right? It's the leading coefficient. So you are correct. So if you are given an equation, the first thing you want to do is you want to sit back for a minute and say, what should my end result look like? My end result should be a parabola, in this case, opening up, because the leading coefficient is 1, right? A, and let me go ahead and just write that down. We might as well. Oops. A is 1. B is what? In this equation? What's
2.
2. And what is C? 0. Very good. Okay, so I have a quadratic equation. I recognized it was quadratic because it has the highest degree of x is 2. I know its graph is going to be a parabola. I know it's going to open up in this case because A is positive. A is 1. So at the end of the graph, that should be true. Now, what do we know about this parabola? Is there anything automatically other than the fact that it opens up, the graph opens up? Is there a point I already know on this parabola?
0, 2.
0, 2? I'm not sure about 0. I'm not sure about that one.
So that's like the y-intercept.
Okay, so the y-intercept is the point on the y-axis. For the point on the y-axis, the x is 0.
Sorry.
0, 0. You got it, Reese. 0, 0. So since C is 0, right? C is 0. I know my y-intercept is 0. Can everybody see that? So finding the y-intercept, 0C, is a good point to have on the graph if it exists. There are instances when the parabola opens to the right or to the left, and it's not a function, but that we don't have a y-intercept. So in this case, given this equation, we know automatically the parabola opens up. 2, we know the y-intercept. Did everybody see how I know those two things? Okay, now, well, some other interesting things that I might want to know about this function, the graph of this function. Don't I care about the x-intercepts? I mean, important things to know are x-intercepts, y-intercepts, certain things like that. So how on earth would I go about finding the x-intercepts? What do I know about all points that fall on the x-axis? What do I know?
Their y value is 0.
Their y value is 0. Beautiful. So if and since this is a quadratic equation, how many solutions should I have? How many, and I'll stick with the word solutions. How many roots should I have since it's quadratic? How many potential values of x?
2.
2, yes. Quadratic means I have 2 roots. Now, those roots may not be distinct roots. I may have a double root. I may even have a complex root, right? It may be imaginary. But I know for my x-intercepts that my y value is 0. So I've plotted my y-intercept. Oh, I kind of already know one of my x-intercepts, right? But let's talk about algebraically how we would find those values. So for x-intercepts, my y value is 0. So I'm going to take this equation and I'm going to set it equal to 0 because that will allow me to find the values of x that make y 0. In essence, that would give me my x-intercepts. So looking at that, how on earth would I approach the right-hand side of this equation to find those 2 values of x? Anybody have any ideas what I could do to the right side of this equation?
Factor an x.
I would factor. I'm going to factor. And factoring skills are ever so important. So if I factor the right-hand side, the greatest common factor, the most I can divide out of each of those is what? And Reese, you kind of already said it. What can I factor out of each of those terms? They each have what? Anybody? Do we know how to factor the right-hand side?
X.
X. Okay, so if I factor out an x, let's see what's left over. X squared divided by x gives me what? X squared divided by my greatest common factor x is what? I'm doing x squared divided by x. If I simplify that, what does that give me?
X.
X, yes. Now I'm looking at this 2x and I'm dividing it by my greatest common factor. And what does that give me?
2.
Excellent. So do you see how I have factored the right-hand side as x times x plus 2? Because if I were to redistribute by multiplication, I'd get this back, right? So we factored the right-hand side. Can everybody, does anybody have any trouble with that factoring on the right-hand side? Speak now or forever hold your peace. Okay, now there is something called the zero product property that says if I have two things or more set equal to 0, that I could go ahead and set each of those equal to 0 and solve for x. So I'm going to take this first one and set it equal to 0, and then I'm going to take that and set it equal to 0. So I have x equals 0, and I have x plus 2 equals 0. Does everybody see how I've done that? I've set each of those factors equal to 0. Now, when y is equal to 0, x is equal to 0. So I have an x-intercept. Well, I already knew that one because I happen to be the y-intercept. But what would my other value of x be when y is 0?
-2 or -2.
Yes, -2. Christopher, excellent. So I have my other x-intercept. So by setting the equation equal to 0, letting y equal 0, I am able to get those two x values that would give me those x-intercepts. Now, one of them happened to be the y-intercept as well. So all I've really gained is another x-intercept. So I know these 2 points exist on my graph. I also know my graph opens up. So I'm almost there. With respect to a quadratic function, a parabola, what is another important value that we would be interested in knowing for a parabola? What is another characterization that we can talk about for a parabola? Does anybody know?
It would be the point in the middle.
Okay, more specifically, so there is an axis of symmetry. Christopher, you are correct. But in particular, I'm looking at that value, that max or that min. What is that point on the parabola called?
The vertex?
Yes, the vertex. Exactly. Beautiful. So how on earth would I be able to find the vertex? Well, these are nice integer values. So I know my graph kind of looks like that, and I know that there is an axis of symmetry, right? If I were to fold my parabola on that axis of symmetry, I would get mirror images. So I know there is an axis of symmetry here, right? At x equal 1. And I know my vertex has to fall on that axis of symmetry. So I could be clever and just use that information to find that vertex, or I could use kind of a formula. Anybody have any ideas how we're going to find that vertex before I tell you?
Well, you already know what x is, which is -2, so you're gonna plug that into the equation.
Okay, it's not -2. The axis of symmetry is in between, right? So what would, Christopher, what would that x value be? If this is -2 and this is 0, what is this x value? Not
For which one?
for the vertex, for our axis of symmetry, right? This is our axis of symmetry. And my vertex falls on my axis of symmetry. So what is the x value of the vertex?
-2.
Not negative.
No.
We're halfway between 0 and -2.
It's -1.
-1, right? Christopher, do you see why it's -1?
Oh yeah, I was just thinking about answering the equation like y equals like -2 squared and all that. So, I don't know.
Okay, you mean for the, okay, I see, for the quadratic formula, for the x-intercepts. So my axis of symmetry is on x equal -1. So my vertex exists, kind of like what Christopher was saying, when x is that value. So I could know that my vertex has an x value of -1, and all I have to do is find the y value. So I could go back to this original problem, the original equation, and I could substitute in x to be -1. I could substitute in -1 for x, and I could find the y. That's definitely one way to do it. So let's go ahead and do that, and let's find the y value. So what is the y value of your axis of symmetry? Negative what?
-1.
-1. So I have my vertex. So if I go to -1, -1, I have my vertex and I can graph it, right? Now, that works great. That's a great way to do it if I have integer value intercepts. But let's say they're fractions or decimal equivalents. We're not going to be able to exactly determine what it is as easily, right? So there's another way that I can find the vertex and plot this point so that I can finish my graph. If you are given the equation in this form and you can identify this information, A is 1, B is 2, in this case, C is 0, there is another way to find the vertex. To find the x value of the vertex, you evaluate -b over 2a. That's how you get the x value. So that would be, what is b? What did we say b was? In this equation, what's b?
2.
2. So I have -2 over 2 times, and what did we say a was?
A 1.
Exactly. So if a is 1, then the x value of my vertex is -2 over 2, which is -1. Look at that. So if it's not easy to identify because it's not in between two integer values, or we don't have those two values for some reason, I can find the x value and then exactly like we did before, take that x value, substitute it back into the equation, get the corresponding y value. So if you can't see it on the graph, this is how you find the x value of the vertex if the equation is given in this standard form. And we have the graph. Shall we try? Are there any questions on this? Shall we try another one? Yes, of course we're going to try another one. All right, I'm going to give you an equation. Here we go. Here's your quadratic equation. I'm going to give you y equals x squared minus 2x minus 3. Now, we know this is quadratic because the highest degree of x is 2. So I know the graph is going to be a parabola. What is the first thing, one thing you can tell me about this graph? What do we know about this parabola?
It opens up.
It opens up. And how do I know it opens up?
The leading coefficient is positive.
The leading coefficient A is 1, A is positive. So does anybody not understand that this parabola opens up? Does that make sense? Okay. What else can you tell me about this parabola, the graph of this parabola?
The y-intercept.
Okay, so what is the y-intercept?
0, -3.
0, -3. Because C is -3 and the y-intercept is 0, C. Does everybody see that? Ariana, does that make sense? Natalie? Can you get this information? Nathan? So far, so good? Okay, now what? If we want to graph it, what are we going to do next? You tell me. I don't want to just keep looking at this equation. Tell me what I'm going to do. I'm going to plot my y-intercept because I know that, right? I know that's my y-intercept. Anybody have any ideas what I could possibly do next? What other information might I want to know?
Find the y-intercepts. Or sorry, the x-intercepts.
Find the x-intercepts. How am I going to find the x-intercepts?
Factor.
All right, going to factor the right-hand side. So I'm looking for 2, potentially, x-intercepts. That's when the y value is 0. So I'm going to set this equal to 0, and I'm going to factor the right-hand side. Abiella, can you give me one of the factors? Do we know how to factor that quadratic trinomial? Do y'all know how to factor this? I want everybody to factor that. And then you can check it, because if you multiply those two binomials together, you should get that quadratic expression on the right-hand side. Factoring is very important. Factoring is huge, right? You saw it in rational functions, polynomial functions. You'll see them in pre-cal. If you can't factor, don't even bother taking calculus.
Is it x plus 1 and x x minus 2?
X minus what?
Oh, no. Is it?
I don't know. You foil and tell me if it is. I'm not going to tell you.
Okay, I had it a minute ago and I just
I'm
forgot.
not letting everybody find the factors. Let's find those factors. You're factoring the right-hand side. You're trying to find 2 little binomials. So that if you were to FOIL, you would get the quadratic trinomial on the right-hand side.
Wait, can I say it?
Has everybody had a chance to factor? It looks like, Reese, hang on. Looks like some people are still factoring. I love that you have it. Ariana, Natalie, are you able to factor? Did we factor? Yes? We got factors? Ariana, did you get factors? Yes? Okay, what are the factors? Go ahead, tell me the factors. Somebody. Ariana?
1 and -3.
I need the entire factor. I need the binomial. We have to be specific. Give me the binomial.
X and the Y is 1.
Well, give me the binomial. Give me the two binomials.
I forgot what the binomial is.
Well, x plus or minus a number.
Can you say that again? I'm sorry.
X plus or minus a number, right? So I should have x plus something and x times x plus something.
Oh, fuck, I forgot.
We'll show it every step. Christopher, we'll show it every step.
X plus 1, and the other one is X -3.
Did we all get that? Eric got it. Christopher, that's perfect. Abiella, Ariana, Reese, did y'all get that? Nathan, could we factor the right-hand side? Yes? Okay, that's the first step. Now, we're going to set those factors equal to 0, right? Because those are the entire, when you're asked for a factor, that's the factor. The binomial is the factor in this case. So what are my two values of x that are solutions? X equal what?
-1 and +3.
-1 and +3. Okay, so I have my x-intercepts. Let's plot our x-intercepts. So I have -1, 0, and I have 1, 2, 3, 0. Now, since those are my x-intercepts, and I know the graph of my parabola is symmetric about the the axis of symmetry, I know my axis of symmetry falls halfway between those two x-intercepts. So can you tell me what the axis of symmetry is? The equation of that vertical line. What is the axis of symmetry? Can anybody tell me?
Is it 1?
Okay, but the value of x is 1, but we have to write it as a line, right? That's a vertical line. So I know if I fold my graph, so that's my axis of symmetry. If I fold my graph along the line x equal 1, because that's, 1, 2, 1, 2, right? That's halfway between those two x-intercepts. Then I have a parabola. Oh, but what am I missing? I can't graph it yet. I'm missing a very important part of this parabola. What am I missing? Anybody tell me? What am I missing?
How far down it goes.
Yeah, and what is that called? What is that point? I'm looking for the vertex. Now you want to find that vertex. Find that vertex. We talked about 2 different ways to find the vertex. Find me the vertex and finish graphing the parabola. Find me the vertex and graph the parabola. Do we have a vertex? We have, Reese has a vertex. Anybody else have a vertex? Did we get a vertex? Eric, did you get a vertex? Ariana, did you get a vertex? Did you find the vertex, Ariana? No, not yet. How are we finding it? Are we stuck? Yes, you're stuck. Okay, we know the vertex falls on the axis of symmetry. So we know the x value of the vertex, don't we? Ariana, what is the x value of the vertex? Based on the axis of symmetry, right? What is the x value of the vertex? Can anybody help out Ariana? I can't hear you. What, say that again, Eric?
1.
It is 1. Ariana, do you see that the axis of symmetry is x equal 1? And so since we know the axis of symmetry is x equal 1, and we know that the vertex of the parabola falls on the axis of symmetry, has that same x value, you can, as we did in the last example, you can just substitute in that x value into your original equation and find the corresponding y value. Who has found the vertex?
That's good.
Who has found the vertex? Eric, did you find the vertex?
No, I messed up.
You messed up. Okay, that's all right. Do you know how you messed up? At least you knew you messed up. Christopher, did you find the vertex?
No.
No. Okay. Abiella, were you able to find the vertex? No. Okay. Do we know what we're supposed to be doing to find the vertex? So we have the equation. We know the x value of the vertex. And since this is a nice little dependency relationship, y depends on x. So if I know that x equal -1, then all I have to do is come into this equation and substitute in -1 for x and find y. Natalie, does that make sense? Okay, so now that I have shown you this step, I expect somebody to be able to find that y value so that we can graph that little vertex and finish the graph of our parabola. So take a minute and let's find the corresponding y value for x equal 1, not -1, x equal 1. So my apologies.
Okay, so I did get it right.
Okay, what'd you get, Eric? What did you get?
+1 and -2.
A -2. Did anybody get a different value for y?
Yeah, I got -4.
-4. Did anybody get a different value for y? Christopher, did you get a value for y? Did I throw y'all off by accidentally giving you that -x? My apologies. We know we're using that axis of symmetry. Let's try it. Who's right? Ariana, did you get a value for y? Did you get the y value of the vertex? Ariana, you look very hesitant. Did you get the y value of the vertex?
I was still trying to solve it.
You're still trying to solve for the y. Okay. Evaluate the right-hand side when x is equal to 1, and let's find y. Abiella, were you able to find the y value of the vertex?
I don't know.
You don't know if you got, did you get a numerical value for y?
Yeah.
What did you get?
I got 0. I don't know.
You got what? Say that again.
0.
You got 0. Okay, so if I'm taking my original equation and I'm substituting 1 for x, shall we do this example together, and then I'm going to give you another one to do on your own. So I have 1 squared, which is 1. Then I have minus 2 times 1. So what do I write next? So that's 1 what? Negative 2 plus times positive 1. What is that going to give me?
Positive 2.
Is it positive 2? No, negative, right? Negative 2 times 1 is negative 2. Do we agree? And then I have my minus 3. So then that's y equals 1 minus 2 is negative 1 minus 3 is what?
Negative 4.
Negative 4. Negative 4. Negative, good. So I can plot that point, 1, negative 4, and then I know I'm passing through, oops, that's kind of hideous. And I can get my graph. Now, can we put this equation in Desmos? Can we put this function, this equation in Desmos and get the same graph? I want you to open up Desmos and let's put in that equation and see if we get that graph. Okay, so we're opening up Desmos. Open up Desmos. And let's put that equation in. So I have y equals x squared minus 2x minus 3. And let's look what we have. That's beautiful. I see my y-intercept. I see my x-intercepts. I see my vertex. That's beautiful. That's absolutely beautiful. Okay, so I'm going to give you another one, and you're going to do a start to finish. We're going to try to do, and Nathan, you missed the graphing. We did this whole graph. Here you don't like to graph, well, you missed the graphing. All right, we're going to do another one. Here we go. I'm giving you another equation. You are going to do your best. Now, this one's a little bit more complicated. I may give you a little hint. Again, we know it's quadratic because the highest exponent of x is 2. So you're going to have to tell me, does it open up or down? I'd like you to identify A, B, and C. Then I would like you to tell me the y-intercept and the x-intercepts. And then I want you to graph it. And then I want you to check your graph after you've given me this information on Desmos. So this is what you're doing. If you get stuck, say something. Don't just sit there. Nathan, here you go. You're graphing, Nathan. If you get, this one is trickier. So if you get stuck, tell me where you're stuck. Any ideas? How are we starting? Can somebody tell me something about this parabola? Can somebody tell me something about this parabola to make sure that we're all on the right track?
It goes down.
It's going down.
Opens down. Very good. And how do we know it opens down?
Negative x squared.
That's right. Our A is -1. So our A is less than 0. Excellent. So it opens down. Good job. Good job, Nathan. That's the first step. Abiella, dare I ask you if we know another point on this graph? Just from the equation, do we know another point? You should be able to look at this equation and tell me another point.
The y-intercept.
Yes! We know the y-intercept. Excellent. What is the y-intercept? You do know it, but do we know it?
0 and -8.
You are fantastic. And we know that because of the C value. That is our constant. Excellent, excellent, excellent. I know that. Very good. All right, here we go. Here we go. I need some X-intercepts. Are we having difficulty factoring the right-hand side? Anybody having difficulty factoring the right-hand side to find the X-intercepts? Anybody? Ariana's okay, Ariana, let's look at this. To find the X-intercepts, I know that my Y values are 0 for those X-intercepts. So I'm going to come over here and I'm going to substitute in 0 for Y. Is that part okay? Yes, okay. Now, personally, when I see a negative leading coefficient, I see a negative here. I like to factor out a negative. I can factor out a negative. If I factor out a negative, what is left over? What is the result of dividing each of those terms by -1? Tell me what those are. What is that? What is this trinomial here once I take this and divide it everything by -1? You tell me.
Is it x squared plus 6x plus 8?
Yes. Ariana, do you see that? Eric, that is correct. Ariana, do you see how I divided each of those terms by a -1, changing the sign of each of those terms? Yes? Now, guess what? You can factor this now. This is a little bit easier to factor, don't you think? A little bit easier to factor that trinomial than the one with the negative. Still works, still gives us those 2x values, because if I divide 0 by -1, it's still 0. So it doesn't change anything. Does that make it a little bit easier to factor? Remember, we are trying to find two binomials that if I multiply them back together, I'm going to get this trinomial. Does anybody think they got the factors? Do we have the factors? Do we know these factors? Anybody?
Is it x plus 2 and x plus 4?
It is. Now, can we just talk about the thought process in case somebody's having trouble finding those factors? Remember, the two numbers you choose to be here have to multiply to give me this, right? To factor. The first term of each of the factors have to multiply to give you this. In addition, these two numbers have to multiply to give you that, right? So we're having to factor 8 to figure out what these two numbers are. But those two numbers also have to add to give me this. Do we remember how to factor? Natalie, yes? We remember how to factor? Abiela, do we remember how to factor? Yes? Did we get those? Nathan, did you get those factors? Okay, so then from there, you should be able to tell me. So now I can take each of those factors. Oh, I don't need the parentheses. Each of those factors and set them equal to 0. So what are my two values of x?
-4 and -2.
-2 and -4. So I have my x-intercepts. Do I have those points? Do you see how I plotted those x-intercepts? Nathan, do you see how to plot those x-intercepts? Now I know it opens down. I know it goes like this and it goes like that and eventually comes down over here. But what other value do I need to know? Yes, yes, I saw your faces answer the question. The vertex. Now remember, the vertex falls on the axis of symmetry. And the axis of symmetry is halfway between those two x-intercepts. So can you tell me the axis of symmetry? What? I'm sorry?
X equals -3.
Is it -3? Oh, wait, did I graph that? I graphed that kind of hideous. Hang on. That's a hideous graph. -2, -4. So yes, our axis of symmetry is in between that, x equal -3. Right? It's in between those two values. So if I have my axis of symmetry, I have my x value of my vertex. So I can then find the y value of the vertex by just substituting in that x value here. Now, you got some negative numbers there, so that can pose a little bit of difficulty. So be very careful with those x values when you're substituting a negative. So I'm coming back to my original equation, and I'm substituting in -3 for x. What is the y value of my vertex? What is the y value of my vertex? Tell me when you think you got it. Y value of the vertex. If actually, don't tell me. Check it on Desmos and see if it's right. Graph it. What is the y value of the vertex? Graph it on Desmos and see if your graph works. Nathan, is this helping with the graphing? Yes? It's a nice procedure that you go through for graphing a quadratic function. Actually, I don't want to give that away yet. Is anybody having trouble evaluating the y value of the vertex? Is anybody having difficulty getting this? Speak now and I'll work through it. Anybody? We're getting it? Does anybody want to tell me what they got? Natalie, you want to tell me what you got? What'd you get, Eric?
I got -3 and +1.
+1. Can we get that 1? Do we need to see how we got the 1? Is this difficult? Shall we walk through this? Yes, no? I know how to do it. I'm happy to walk. Yes, you want to see it. Okay. So I have a negative here. And then if I evaluate -3 squared, -3 times -3 is a +9. And then -6 minus 3, if I multiply those, I'm going to get a +18 and then a -8. Okay, so this minus sign comes down, and the -3 squared is a +9. So that's why I have a -9 here. And then if I continue to work left to right, -9 plus 18 is 9. 9 minus 8 is 1. So the y value of the vertex is 1. So I have that point, -3, 1. I have the graph, but you should be able to see it in Desmos. Do we need another one to practice? Raise your hand in Teams if you want another one to practice. You got it? You don't want another one? You got it? You don't want, Eric does not want another one. I'm happy to continue working these to make sure you understand them. Okay. If you really don't want another one, we stop. We continue to move on. Okay, so the next thing that I want to talk about, we've talked about a couple of types of functions. And I would like to start building our library of functions. And so in our packet, I start talking about parent functions. So there's lots of functions that were discussed in Algebra 2. So let's just kind of look at these stripped and down basic parent. They're called parent functions. They are the simple functions that we can transform. We can shift them left and right horizontally. We can shift them up and down vertically. We can reflect them across the y. We can reflect them across the x. We can vertically stretch them. We can horizontally stretch them. We can vertically compress them. There's lots of transformations that you should be able to recognize from the equation, but also describe. And so before we can talk about transformations, we need to look at the most basic form of some of these functions. So these basic forms are called parent functions. So given a function, you should be able to recognize the underlying parent, the simplified form, the most simple form of that function. So let's build our library. The first parent function I would like to talk about is the constant function. It is represented by we can either write y equal x or f of x equal x. So it depends on whether you want to write it in function notation or not. Now, that x on the right-hand side is just a constant. If I can stop writing, it's just a constant. It's just a number. So if I'm looking at y equals some constant, some number c, or f of x equals some constant c, this notation here is just telling you that c is an element of the reals. So if I am trying to graph this, no matter what x value I choose, the output is always the same constant c. So it doesn't matter what values of x I put into the function, the output is always the same number. So if I'm looking at the graph of a constant function, y equals c, can anybody tell me what that graph would look like? What type of graph is the graph of any constant function? Y equals c.
A line, like a straight line.
It is a line, and what type of line more specifically is it?
A horizontal line.
It is a horizontal line. So the constant function is a horizontal line, and it is at whatever that value c is. So if I say c equals 3, it would be this number, right? Because no matter what point I choose on this line, the c value is the same. Okay, so that is my constant function. So tell me, what is the domain for any constant function? In an as represented as an interval, what is the domain? What is the domain of that constant function as an interval? What is the smallest x value it takes?
Negative infinity?
Negative infinity, yes. And what is the largest x value?
Infinity?
Infinity, that is absolutely correct. Now, what about the range? What is the range of this constant function? I'm looking at y values, right? Range is y values. So what is the range? Well, what is the y value for every one of these points? It's the same value, right? In this case, it's 3. But for any constant function, it's just c, right? It's just that one value, right? Does that make sense? In this case, c is 3, but it's just that c value. Doesn't have any larger y values, doesn't have any smaller y values. Okay, now let me ask you this. Are you familiar with what it means for a function to be increasing, decreasing, and constant? Have you heard those terms? No, you haven't? Okay. A function is said to be increasing if it rises left to right. So in other words, if I'm looking at it, is it going up? It doesn't have to be a line, but if I were to draw it, are the y values getting larger and larger and larger? Well, I don't see my y values changing, so it's not increasing. Now, based on what I said, what it means for a function to be increasing, let's take a look at, is it decreasing? Well, what does it mean for a function to be decreasing? The y values decrease, get smaller, left to right. Well, again, the y values don't change for the constant function. So if I have a function where the y values are the same over an interval, we would define it on that open interval, right? So we always use open intervals when defining where a function is increasing, decreasing, or staying constant. So where, over what interval does this function stay constant? Over what interval does this function stay constant? Can anybody tell me?
3.
Well, intervals define domain values. So if I look at the x values for which this function is constant, isn't it all real numbers? Isn't it always constant? I mean, it's a constant function. So since it's a constant function, by definition, it's constant over the entire open interval. Okay, now let's look at the second type of function. The second type of function is known as the identity function. And we represent the identity function as either y equal x, or using function notation, f of x equals x. So let's think about the points that fall on the identity function. It's saying that the y value equals the x value. So I could make a table of values, and I could substitute in for x values and see what the corresponding y values would be. So if I look at this function, the identity function, because the x value is the y value, if I substitute in -2 for x, what is y in the identity function? Somebody tell me. Anybody? If I substitute in -2 for x, what is y?
-2.
It is -2. Okay. Well, what if I substitute in -1? Can somebody else tell me what the y value is if I input -1 in for x into the identity function?
-1.
Exactly. Well, in fact, this is true for every y value. It is the x value. So I could plot those points. -2, -2, -1, -1, 0. Oh, and so we see the graph of the identity function. Now, this hopefully you recognize as a very important line in Algebra 2. Maybe this makes you think about taking the inverse of a function. And we will talk about that, but perhaps this is kind of making you think about taking inverses of functions, reflections across this very special line. So let's talk about the domain of this parent identity function. Can somebody tell me what the interval is for the domain of this identity function? Anybody? Tell me the interval for the domain. Nathan, Natalie, anybody? Can anybody tell me the domain values, the interval? What's the smallest x value? Natalie, I see you're moving your lips. Say it. What is the smallest x value?
Would it be -infinity?
It would be -infinity, absolutely. And what would the largest x value be in the domain?
Infinity?
Beautiful. That is absolutely correct. So the domain for your identity function is all real numbers. What about the range? What would the range be for the parent identity function? Ariana, Abiela, Christopher, do we have any ideas? If I'm looking at the range, the y value, what is the smallest y value that this graph takes on?
It's -infinity to infinity.
It is -infinity to infinity, right? Because it goes on forever and ever and ever. There are no restrictions on x or y in that case. Now, based on what we said, it means to be an increasing function. Let's talk about the open intervals, if they exist, for where the functions are increasing, decreasing, or constant. Over what open interval? Because remember, we always define increasing, decreasing, and constant on open intervals. That's the definition. Where is the function increasing? It's kind of tricky. Where is the function increasing? In other words, it's rising left to right. Y values are increasing left to right.
-infinity, infinity.
Beautiful, beautiful. It's always increasing, right? As I increase my x, my y is increasing. In fact, with a slope of 1, right? A constant rate of change. Now, is this function ever decreasing? If so, what interval? Is this function ever decreasing? Are y values ever getting smaller as we increase our x values? Nathan? Yes, no, maybe so? Okay. If I say that the function is increasing over all x values, can it ever be decreasing? No, because I just said it was always increasing. So never, right? And it can never be constant. Now, when we were talking about those piecewise continuous functions, we can have one part that is increasing, another part that's constant, and another part that's decreasing, right? If it was defined piecewise continuously. But in this case, it's just one continuous function defined with one rule. So we can only be one of those. Okay, let's move on to the next function. Now, Eric, you were clever when you saw this, right? When we talk about the absolute value function, most of the time people see it as is written this way. But remember, it can be represented as a piecewise continuous function over two different domains. So for x is greater than or equal to 0, it's going to be y equal x. For x less than 0, it's going to be y equals negative x. So if you can't remember what the graph of this parent function looks like, you can always create a table of values. So let's say I pick some x values and I substitute it into this function. So let's pick -2. Let's pick x equals 0. Let's pick x equal 2. And since it's defined for all real numbers, I can choose any x's I want. But perhaps since I see that it kind of changes at x equals 0, I do want to make sure I include that, because that's going to be where the graph kind of looks a little different. So, which equation, the first one or the second one in this piecewise continuous function, which function would I use to evaluate x equal -2? Would I use the first one or would I use the second one? Anybody?
Second one.
I would use the second one. You are absolutely correct, because that is when x is less than 0. So -2 is less than 0. So if I substitute into the second equation, y equals -x, when x is -2, what is y? I'm using y equals -x. So if x, that's tricky, if x is -2, what is y? Ariana, do we know? No. If x is -2, if I substitute in -2 for x, minus a -2 gives me what? What is y?
2.
It's 2.
It's just +2, right? So when x is -2, I'm using the second equation. I'm substituting in that x value into the equation and I'm getting the y. So I have a point. -2, right? The ordered pair is -2, 2. So I can go to x equal -2, y equals 2. I have that point. That point exists on this graph. Now, which equation, and this is a little tricky, which equation am I going to use to evaluate x equals 0? Am I going to use the first one or the second one? Which equation is valid for when x is equal to 0? The first one?
The first one.
The first one, because do you see that or equal to? You see that or equal to? That's saying use me if x is equal to 0 or greater than 0. So if I substitute in 0 into y equal x, right? Because now I'm using the first equation. If I substitute in 0 for x, Ariana, what is y? If I substitute in 0 for x into this equation, what is y?
Is it 0?
It is 0. Yes, it is. It is. That is correct. Trust yourself. So I have the point 0, 0. Okay, now let's see which equation we're going to use to evaluate x equal 2. Am I going to use the first equation in green to evaluate when x is equal to 2? Or am I going to use the second equation in blue? Am I using the first or the second one to evaluate x equals 2?
The
The
first.
first.
The first one, because again, x is greater than or equal to 2 says, hey, use me. So again, I'm going to substitute into y equal x. I'm substituting in 2 for x. So what is the output y when x is equal to 2? Abiela. If I'm substituting in 2 for x, what is y?
2.
It is 2. You guys, you got to be a little bit more confident with yourselves. So now I can plot that point. And if I connect it, I have the graph of the parent absolute value function. There is the parent absolute value function. Now again, on Monday, we're going to talk about what happens when we transform it, when we horizontally shift it left or right, vertically shift it up or down. We're going to do a lot of transformations. Have y'all heard of the transformations? Does that sound familiar to you? Eric says yes. Christopher, have you heard of about Nathan says yes, we have. Okay, y'all. Ariana, we've heard of transformations. Natalie, okay. You know, you said you weren't comfortable with graphing, so we're going to be playing with transformations on Monday. Something to look forward to. Okay, now let's talk about how to represent the intervals for each of these if they exist. So the domain, we can state the domain as an interval. What is the domain of this parent absolute value function? Domain as an interval. Can anybody tell me?
Negative infinity to infinity.
Exactly, right? Because it goes on forever and ever and ever to negative infinity. And then it goes on forever and ever and ever to positive infinity. What? Okay, be careful. The range. So I'm reading my y values for which this graph exists. What is, and be very careful, what is the range?
0 to infinity.
And does it include 0?
Yes.
Yes, it does. So it'd be a closed bracket, right? So if I read the graph, the smallest y value is 0 and it is included. So I have a closed bracket and then it goes up and up and up to positive infinity. Ariana, does that make sense? Yes. Okay. Now, here we go. Let's see if the function is increasing, decreasing, or constant. And remember, we always define those on open intervals. Now, increasing, y values getting bigger. Can you tell me the interval for where the what? And remember, the interval is defined over the domain values. What is the interval where this function is increasing? Can anybody tell me? Where is this function increasing?
0 to infinity.
That's beautiful. That is absolutely correct, Reese. Now, how did we find that? We're looking for when the function is, I want to do it in a different color. Heaven help me. There we go. I'm looking for where the function is increasing. So the y values are getting bigger on that interval, right? It's this interval here. That interval is 0 to infinity. Only in this interval are the y values getting larger. Does that make sense? Natalie, does that make sense? Abiella? I mean, I like to look at the graph and I like to highlight. No, Abiella says no. So I'm looking for when my y values are getting bigger and bigger and bigger. Here my y value is 0. Here my y value is 1. Here my y value is 2. Do you see how my y values are increasing? As I go to the right, as my x increases, my y increases, right? So if I'm talking about where a function is increasing, I'm looking for when it is going up. Now, it doesn't have to go up linearly. It could go, well, I don't want to be specific like that, but I mean, that's also going up, right? So if you look at the graph and you look for where you're rising from left to right, that is where the function is increasing. So only from x equals 0 and then forever to the right to positive infinity is it increasing. Abiella, does that make a little bit more sense? A little bit?
Yeah.
Okay, then let's see if we can apply this thinking to where it is decreasing. So again, I'm looking at the function and I'm looking for where it is falling left to right. So where are my y values? Over what interval are my y values decreasing? If I look at my graph, isn't it here? Aren't my y values getting smaller and smaller and smaller over this interval? Abiella, does that make sense by looking at the graph? Does that help to look at the graph? Ariana, does that make sense? Then can you tell me where is this function decreasing? Over what interval is this function decreasing? Anybody?
Negative infinity to 0.
Beautiful. And again, it's over defined on an open interval. So from negative, because forever and ever and ever and ever, all the way up to 0. So it's over this interval here that the function is decreasing. Is it ever constant? Is it ever a horizontal line? No. So never. Let's look at more parent functions. Let's look at more and let's reinforce this. So the next type of parent function that I want to look at falls under the family of power functions. And we've been working with these power functions, right? We worked with linear functions where the exponent, the power was 1. We looked at power functions, quadratic power functions, when the exponent was 2. We even kind of mentioned cubic power functions when the exponent is 3. Let's talk about what the graphs look like and describe some characterizations, domain range, increasing, etc. So quadratic power function. The parent quadratic power function is y equals x squared, or using function notation, f of x equals x squared. Now, you already talked about how it's a parabola, and it opens up or down, depending on the leading coefficient. We played with that a little bit this morning. If I want to substitute in some x values, can you tell me the corresponding y values? So I'm making a table to help me graph it. So when x is -2, what is y? Anybody? When x is -2, what is y?
+2.
Not +2.
Is it? Oh wait, no. I mean +4. Sorry.
+4. Yes, Eric. +4. So I can plot that point. Because remember, if we square any negative number, it becomes positive, because a negative times a negative is a positive. What about if I substitute 0 in for x into this parent quadratic function? What is y?
1.
0. So it passes through the origin. And what about when x is 2? What is y?
4.
4. Very good. So I can plot that point. So I have my parent quadratic function. Now, let's talk about the domain for every parent quadratic function or any quadratic function. What is the domain as an interval? Can anybody tell me? Nathan? What is the domain of this parent quadratic function as an interval? What is the domain?
-3 to 2.
Okay, well, but it goes on forever, right?
Oh yeah, and -infinity to infinity.
Beautiful. Beautiful. All right. What about the range? Can somebody tell me about the interval for which the range exists for this parent quadratic function? Anybody?
Close bracket 0 to infinity.
Excellent. This is the smallest y value, right? Y equals 0. And that point exists on the graph. And then all y values greater than that. Excellent, excellent, excellent. Okay, here we go with our increasing, decreasing, or constant. Remember, always define on open intervals. If you need to highlight, by all means highlight where you think it is increasing. So
How do you get the close bracket again?
the closed bracket exists for domain and range. So intervals for which a value is included. So in this case, infinity is always open. You always use an open bracket for infinity. Now, since this point exists, when defining the range, I'm going to have a closed bracket at 0. If it were an open point, then I wouldn't include it. But if it's a solid point, if it's on the graph, it is included, so it's closed. Infinity is always open, and where you define increasing, decreasing, and constant is always open. Does that help? Okay. Where is this function increasing? Can anybody tell me where this function is increasing? Anybody?
It is increasing on negative infinity to infinity.
You think so? If I go from here to here, the y value is getting bigger or smaller?
Oh, I was thinking about the x.
That's domain. But if we're thinking about where it's increasing, remember, our y values are getting bigger. So it's increasing when our y values get bigger as our x values get bigger. So where is it increasing? How would I define that interval? It's from here, there, right? That's where it's increasing, isn't it? How would I define that interval?
0 to infinity.
Beautiful, 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 Ariana, beautiful. Now, where is this function decreasing?
Negative infinity to 0.
Beautiful. Do y'all see that? So it's rising. The y values are getting larger as the x values are getting larger over here. And the y values are getting smaller. It's falling as the x values are getting larger to the left. Is it ever constant? Is this function ever constant? Is there ever any horizontal? No, never. Good. All right, do we know what the cubic function, parent function looks like? Do we know that off the top? Can anybody describe that? Do you remember that from Algebra 2? That's okay, because we can make a table of values. So let's look at the cubic parent function. Again, I know it's cubic because the highest exponent of x is 3. So it's a cubic parent function. Now, I don't have any restrictions on my x, so I'm going to try, I don't know, -2, 0, 2. Why not? If I substitute in -2 for x, what is the corresponding output y? So I'm cubing -2. What do I get? If I cube -2, -2 times -2 times -2.
6.
No.
-6.
-8.
Let's expand it, shall we? I love that you're answering, but let's see why answers are right. Yeah. Okay, so -2 times -2 is a +4. +4 times -2 is a -8. So -8. What about when x is 0? What is y? Christopher, redeem yourself.
0.
There you go. What about when x is 2? What is y?
8.
8. Okay, so let's plot these points. So I have -2, 1, 2, 3, 4, 5, 6, and I can go off the graph because this Cartesian plane goes on forever. And then I have 0, 0, and I have 2, 8. Now the question is how we connect these points, because it's not a line. In fact, I could put in more values. I could say, what if it's -1? I'm going to get -1. And what if I put in 1? I'm going to get 1. This is the graph of your parent cubic function. Do you recognize that? Have you seen that before? Yes? Okay, we've seen it. So there it is. A little bit trickier now. Here we go. What is the domain of the parent cubic function? As an interval, what is the domain?
-infinity to infinity.
Excellent. That is fantastic, Natalie. What about the range as an interval? What is the range? The range. Nathan, do we have an idea? The range of the parent cubic function?
-infinity to infinity.
That is absolutely correct, right? Because it keeps going down and it keeps going up. Now, here we go. This is kind of tricky. Where is it increasing? Is it? If so, where? Where are our y values getting bigger as our x values are getting bigger? And maybe looking at the table of values wouldn't hurt. Where is this function increasing, if ever? Where? Any ideas?
Is it negative infinity to infinity? Like,
Eric, you are correct. It's always increasing, right? Y values are getting bigger as I'm moving to the right in my X values. Excellent, beautiful. Do you all see why it's always increasing? Yeah? So is it ever decreasing? Is it ever decreasing? Christopher, any ideas? Is it ever decreasing?
no, it's never decreasing.
How can it be if it's always increasing? It's never decreasing and never constant. If it's increasing, decreasing, or constant on the entire set of reals, negative infinity to positive infinity, it can't. It can't be doing anything else, right? Now, there are more power functions. There are more parent functions we can talk about, but I'm thinking about, well, do I want to talk about these? Well, sure, why not? Let's do it. Let's do it. Square root function. Parent square root function. Now, we talked about how to represent a radical using rational exponents. I can rewrite this as x to the 1/2 power. So, and that's just kind of an aside. But let's look at this. If I were to start do we know what the graph of this looks like off the top of our heads? Does anybody know? No. No, that's okay. We can substitute in values. But we have to be careful about the values that we choose to substitute in for x. What kind of values can we substitute in for x? Are there any restrictions on those values? Can I pick anything? Can I choose any number I want to substitute in for x and it would be defined over the set of reals? Or do I have to, can I choose 4? Is that valid? Yes. Okay, so if I substitute in 4 for x, what is y? If I substitute in 4 for x, what is y?
Two.
2. Okay, good. Can I substitute in 0 for x? Can I substitute in 0 for x? Is it defined? Is the square root of 0 defined over the reals? What's the square root of 0? Ariana, do you know what the square root of 0 is? No? Does anybody know what the square root of 0 is?
Is it 0?
I'm sorry, Reese?
Is it 0?
It is 0. So I know this point exists, right? 0, 0. And I know the point 4, 2 exists. Okay. Can I substitute in a negative number for x and have it defined with an output that is a real number? Can I take the square root? No, I cannot. 0 is the smallest value that I can substitute in to the square root parent function and have it defined with an output that is a real number. Because what happens when you take the square root of a negative number? Do you all remember from Algebra 2 what happens when you take the square root of a negative number? What kind of number is that? Anybody remember?
Imaginary?
It is imaginary. So since we're graphing on the Cartesian plane, that doesn't include imaginary numbers. Good, Nathan. So I have to limit it to positive real numbers or 0. But the question is, what does the graph of this look like? The graph of the parent square root function looks like that. The little hint is it's that part of the parabola if it were to open to the right. Why is that? Because if I were to square each side, I would get y squared equals x. So technically, it's that upper part of the graph of a parabola where the y term is squared. Okay, so it doesn't really include this, but I wanted you to see where it came from. Okay. All right, so let's talk about the domain of the parent square root function. What is the domain as an interval? Can anybody tell me what the domain is?
Is it 0 to infinity?
And does it include 0?
Yes.
So we have to put a closed bracket, right, Christopher? Does that make sense? We're putting a closed bracket there because it includes 0.
Yeah, I get it.
Okay, then tell me, what is the range of the parent square root function?
Zero to infinity again.
Beautiful, and it includes 0, right?
Mhm.
That 0.00 does exist. Here we go. Let's define the open intervals for which the function may be increasing, decreasing, and or constant. Is the function increasing? If so, over what open interval? Where is it increasing?
0 to infinity again.
Again, and it's over an open interval. Is it ever decreasing? No, you are correct. Good job, Ariana. Is it ever constant? No. Excellent. All right, let's move on to the parent cube root function, where the root index is 3. So we're now taking the cube root. So this little number here is your root index. So I could rewrite this if I wanted to as y equal x to the 1/3 power, if I wanted to represent it with a rational exponent. And now let's think about this cube root. Well, let's make a table. And let's be very clever. Maybe you want to choose perfect cubes to make it easier for us to evaluate the cube root. So maybe cube root of 0. What's a perfect cube? Can anybody think of a perfect cube?
8.
8 would be a very good perfect cube. Yes. So what is the cube root of 0? What is 0 to the 1/3 power?
0.
0. What about the cube root of 8?
2.
Is it positive 2? Yes, it is. So I have the 0.00 and I have the 0.82. 1, 2, 3, 4, 5, 6, 7, 8. Now, dare I ask you, can I take the cube root of a negative number? You said I couldn't take the square root of a negative number and have it be a real number. Can I take the cube root of a negative number and have it equal a real number? Do we know? If you don't know, care to conjecture if it's possible? Can you guess if it's possible? What do you think? Who thinks that you can take that? Raise your hand, just physically. Raise your hand if you think you can take the cube root of a negative number and have it defined over the reals. I'm the only one. Eric and Christopher say yes. So and Reese says yes. So the rest of you say no, you can't do it. Well, guess what? If I were to take the cube root of -8 and start factoring that, well, That would be -4 times +2. Let's see. Well, what happens if let me factor it with taking out the negative. Isn't it true that I can rewrite 8 as -2 times -2 times -2? -2 times -2 times -2 is in fact -8. Remember, the root index tells you how many of the same base factor you have to have repeating to be able to take one out, and then the rest of that set disappears. So the cube root of -8 is -2. You can't take the square root or an even root index of a negative number. It becomes imaginary. You can take the cube root or the odd root index of a negative number. So this point does exist. So what does the graph of the parent cubic function look like? That. Now, what does that kind of look like? Well, if you think of y equal x cubed, which looks like this, if I were to cube each side here, I get this. You see the relationship? It's kind of nice. It's kind of nice. All right, looking at the domain of this function, this parent cube root function, what would be the domain represented as an interval of this cube root parent function? What's the domain? Anybody?
All real numbers.
It is all real numbers. Mhm. What about the range? Again, for the range, investigate the y values. What's happening? Range values, range values. What y values does the graph of this function does it exist? Does it take on?
It takes on our real numbers.
Yes, all real numbers. Okay, are we ready to describe open intervals where the function is either increasing, decreasing, and or constant? Where is this function increasing? Where are the
All real numbers again.
all real numbers, right? The y's are getting bigger and bigger and bigger. Look at your range. So all real numbers. So can it be decreasing or constant ever? No. Mm-mm. Okay, we're gonna pick up on the other parent functions later in the packet. So we're not gonna do the last couple of parent functions, the last two parent functions, because these are the ones that we've kind of covered so far. So what I would like you to do now is I'm going to ask you to go into Teams. Since this is the end of the first week, I would like you to go into Teams and go into the general section of Teams, and I'm going to try to show this with you. I'll show this to you if it lets me. So let me stop this and go back to Teams. Okay. Actually, I'm going to stop presenting on this one and go to presenting on this one. Okay. All right. All right, so if you go into Teams, oops, and you go into Files, can you see what I'm showing? Yes?
Yes.
Okay. I would like you, if you wouldn't mind, there's a little feedback sheet. So let me explain to you how you're going to have to complete this and send it. This is for me, okay? So I would like you to go to files in general. So everybody do this at the same time. Go to files, look at end of first week feedback. Select it and download it. Okay, so you're gonna, everybody select end of first week feedback and download it. It should download it, and I don't know where you have it saved on your computer, but I want you to open it. And then let me just show you what's in here. Okay, so this is the end of week. Can you access it? Do you have your personal copy that you've downloaded? If you're having trouble, let me know, because I can always post this in the chat as well. Okay, so please type your name. And then I would like you to save it, because you've downloaded it locally onto your computer. Save it with the name and then put a little underscore and then your initials. Okay? Then I want you to describe at least one topic that we've covered this week that was completely new. You think you've never seen it before. And if there's more than one, please list everything you think you didn't see in your Algebra 2 course, or ever, Algebra 1 even, right? Then I would like you to, I'd like you to describe at least one topic that was not new, but you think you understand better now that we've reviewed it. Anything that you think was helpful. And if there's more than one, by all means. Then I want you to describe the most interesting or helpful thing that we've covered this week. What was the most interesting thing to you, or you think has really impacted and will help you? And then describe what you like most about this class. And it could be anything, and I don't really want to put ideas in your head, but you know, that it's small, or that you have time to work on things, or that you feel comfortable to make mistakes, whatever. What do you like most about that? Or you just like math and you love doing math with us this summer? Whatever. And then if there's any other suggestions on how this could be improved. So like next week, I have an idea of what I want to do next week, but if you have any constructive criticism or any suggestions, please type it here. I will not get offended, okay? So fill this out, and then you're going to have to save it again by adding your initials at the end. And then once you've done that, once you've saved it, you need to come back here, okay? You're going to have to come back here and you're going to have to upload it, okay? You can technically drag and drop and it will upload it as well. But I need you to change the name by putting your underscore and your initials, or it will just, you know, copy over the same. If it has the same name, it's just going to keep replacing that file. Does that make sense? Yes? Okay. Is anybody unable to download this on their computer? Everybody got it? Okay. Take some time to complete this. When you complete this, you know I'm showing you another puzzle. So after you have completed this, go ahead, take a peek at this puzzle and tell me what you, I don't want to share it yet until you've had a chance to work on it. So I'm going to give you a few minutes. When you finish, and I'll be able to see that you uploaded it. When the first person has finished, and I want thoughtful feedback, so please, you know, be very explicit. I will show you the next puzzle. Actually, I'll go ahead and show it, but please complete this if you don't mind. I appreciate it. So we're completing the feedback, saving it with a different name, and uploading it. And then we have that puzzle. I'm going to run to the facilities while I give you a chance to do the feedback form. Thank you. And feel free to refer to your notebook if you need reminding of what things are called. Once you finish completing it, go back to files, make sure you save it with a different name, go back to files and upload it there.
Miss, I wasn't able to download it.
You weren't able to download it. Okay, let me go ahead and save it in the Teams chat. Let me just post it there. Okay. Okay, so I am going to save it in our Teams chat. Okay, where do I, there's the chat. And then let me save it. Where is it? Where is it? End of first week feedback there. Why is it not letting me save it? Why is it not letting me save it? Let me try attaching it this way. Upload from my computer, desktop. Let's try that. Why? It's what? It's not letting me. Is anybody else having trouble downloading it? Oh, the issues I have. Hold on.